Alright, let's talk about optics. We're going to start in on chapter 22. What we're going to cover is basically sections 1, 2, and 3, talking about mirrors. Now, when we talk about optics, we're talking about specifically geometric optics, or ray optics. So ray optics is going to allow for a couple things to happen, and that is that light is going to be able to be reflected or refracted. So now what this means, messing with me here, OneNote. Don't do this to me. Alright, we have rays of light. They're going to leave an object. You know, light shines on something, whatever, it scatters off. We have light going in every possible direction. These rays of light, when they encounter something else, we're going to focus on cases where they can reflect off of it, if it's a reflective object, shiny, like a mirror. Shockingly enough, talking about mirrors. Or they can be bent by light. That's going to be what we talk about with a lens. For us right now, reflection is what the name of the game is. So now we have a simple law for reflection, and that basically says that the angle that the light makes with the mirror coming in is going to be the same angle the light makes with the mirror going out. From this law of reflection, we're going to get rules for talking about what happens to the image formed by a mirror, if it's planar or if it's spherical. So let's move right into plane mirrors. In plane mirrors, I don't know why everything's so jittery today, we have a plane. So plane in the kind of sense that it's flat. And we're going to have an object. We're always going to have an object. We want to be able to talk about our object in a couple of ways. The object is going to be some distance from the mirror. We're going to call that S, our object distance. Our object is going to have some height. It's not even close to a straight line. That we're going to call H. Now I want to know, what am I going to see when I look in this mirror? So I want to ask, where is the image of this object going to be? I might ask, where is it? How big is it going to be? What's it going to look like? So we can talk about how to find this image. And what I'm going to do is something that's kind of clever. I'm going to locate a point here at the top of this object, and I'm going to locate a second point at the bottom of the object. I could also locate every other point on the object, but that's going to take too long. I want to try to get this done in, just a few minutes. Now, from these points on the object, I'm going to have light shining off of this object in every possible direction. Again, not in infinite amounts of time, so we're going to restrict ourselves to just looking at 2 rays of light. So let's draw one of these. This ray of light is going to leave this object, and it's going to go and hit this mirror. Hit the mirror. Not quite where I wanted to hit the mirror. Nope. There we go. So now when the light hits the mirror, it's going to bounce off. It's going to bounce and be reflected the exact opposite angle. So if it went up 2 and over to the mirror, when it comes out, it's going to go back and up 2 more. So the reflected ray of light is going to go something like this. Now this ray, the one that's leaving the mirror, it looks like it came from over this on this side. So what I'm going to do is extend this ray back. Try to actually draw it in the direction it's supposed to go in. I'm going to extend it back into the mirror, and I'm going to use these dashed lines to help me remember that there's not actually light leaving the mirror from like inside of the mirror. That's creepy. Now, so anywhere along this line is where the light seems to have come from. So to find out where along it, I'm going to draw a second ray. I'm going to go here. This looks like down, 3? 1, 2, 1, 2, 3. Yep, so I got to go down 3 more. 1, 2, 3. Boop. So ray going in, ray going out. This ray that's going out looks like it came from, it's coming from inside. No, alright. Looks like it came from about over here. So now if I look at this object is 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes away from the mirror. This image is 1, 2, 3, 4, 5, 6, 7, 8, a little less than 9 boxes away from the mirror. Wonder if that's significant. Now, I'm going to try to locate the bottom of this. I could locate maybe all 4 corners to help get a sense of where it is, but I'm just going to locate these 2 because, again, only so much time in the day. Ray goes in, went over to the mirror, up 2. Ray goes out, so it's going to go up 2 more. You'll notice the graph paper really helps to make this something that's doable. Although using like a card as a ruler on my computer screen is making it a little more challenging than it has to be. I realize you guys are seeing like the menus popping up all the time. I can't see that so easily because my card is covering it up. Alright, so again, the ray that left the mirror looks like it came from somewhere inside the mirror. So I need to get one more dot on this thing to be able to pinpoint exactly where. So let's see if I go for here. Boop. So that went down 1, 2, 3. So I gotta go down 1, 2, 3 more. And not take my whole screen away with it. And then I connect the dots. And God, it's a global conspiracy. No, it's not actually a global conspiracy. I'm just extending this line back into the mirror. And right around there. In, out. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9 away. 1, 2, 3, 4, 5, 6, 7, 8, 9 away. So it looks like I have an image inside of the mirror. And it's about the same distance and about the same height as my object. So this image distance I'm going to call S prime. And you know, if this is really the height that I'm interested in. So the height of this image I'm going to call H prime. So there are a couple things we can do to talk about this image. We can characterize it in a few ways, about its type, its orientation, and its size. So now for its type, is it real or is it virtual? Well, the image is not actually, you know, these rays of light that are leaving here, they're not actually leaving the image, they're leaving the mirror. They appear to come from the image. So this is going to be an example of a virtual image. Anytime we have these extended rays of light, that's a good sign that it's virtual. We can ask, is it upright or inverted? Well, the top of the object is also the top of the image. Bottom of the object is also the bottom of the image. So this is an upright image. And we can also ask about its size. Is it magnified, shrunk, or unchanged? Well, by inspection, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. H is about 11 blocks, and H prime 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 blocks. So its size is unchanged. We're going to be able to do this for any image we produce, whether it's from a plane mirror, a lens, or a spherical mirror, which is what we're going to come to next. We have two types of spherical mirrors, a concave mirror and a convex mirror. Concave, because it caves away from you. Convex, because it convexes towards you. Continuing. A little more goes into setting up a problem with a spherical mirror. So I'm going to draw it out like this, and there are a couple things we need to label. We have here the principal axis. This is this line that goes through the center of curvature of the mirror. So it's a spherical mirror, right? So it's got a center. That's what C is. If I were to draw the circle that kind of this mirror came from, that's the center of it. And also goes through the focal point. The focal point is half the radius away, and is going to be important for us kind of optically. So the geometry of it is a little intense. We're not going to get into it fully. You can follow along in your book if you really like similar triangles. When we have these, we're going to then have this distance from the mirror to the focal point. This distance right here is the focal length. And the distance from the center to the mirror, this distance right here, that is just the radius of curvature, or the radius. Now, let's take a look at an example like this. I've got an object chilling out here outside of C, and I want to know where is the image of this object going to be. And so we could do this crazy stuff that we were doing up here with the whole like angle in, angle stuff, but like, ooh, curved mirror is really tough to do. You have to talk about the normal, local to it, and like too much. So there are three special rays we're going to draw. One special ray is going to pass through the center of curvature. One special ray is going to pass through the focal point, and one special ray is going to go parallel to the principal axis. So let's do the first one. First one's going to go through C. So I'm going to line up this point here, and I'm going to regret this immediately. So this one is not helpful. It's going to go through C. And then the slight problem is that it's not going to hit the mirror. So we'll leave that one alone for now. The basic idea, if something goes through C, it goes back, it reflects directly back along this line. So that's useful for us. Somewhere around here is where I expect my image to be. The second ray that I want to do is going to go in through F. So again, I'm going to connect the same point on my object, the focal point, and the mirror. I'm going to draw a ray that goes straight in, right at the mirror. This one, so the one that goes through C bounces straight back undeflected. The one that goes in through F is going to bounce out parallel to the principal axis. So it's going to get a nice horizontal line coming out from this. That's mostly horizontal. So right now it looks like the top of this thing should be around here. But we're going to draw one more ray to check. And that's the ray that's going to go in parallel to the principal axis. Now, if you're exceptionally keen on patterns, you might guess what direction the reflected ray is going to go. And that is out through F. Out through F. Oh my goodness, would you look at that? It intersected the other ones. How shocking. It was planned. So that's why you can draw any two of these three rays is enough to locate this. And this right here is the location of the image. Now, if we look at this, a couple of things are going to happen. First of all, we can ask again, is this real or is it virtual? This is a real image because it's produced by the rays that left the object. There's none of this extending backwards stuff. We can ask, is it upright or inverted? Well, the thing that was above the axis is now below the axis, so it appears to be inverted. I should point out, a point that's on the axis stays on the axis, so that's how I knew where the bottom was. And I can ask, is it magnified or is it shrunk? Well, this one appears to be 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes big. This one is 1, 2, 3, 4, 5, 6, 7 boxes big, so it's shrunk. All right, so through C is undeflected. Bounces straight back. Through F goes out parallel, goes. And goes in parallel, goes out through F. All right, let's take a look at one more example of this. Now this is for a convex mirror. You'll notice for a convex mirror, the center appears to be inside of the mirror along with the focal point. I've already drawn my three special rays to start, and I've stopped them when they hit the mirror. So the first special ray was going in through C. So it's going to keep on going. So it's going to go in along this line and then bounce out along this line. The blue one, the second one, the one that went in through F, is going to go in, aim in for F, and is going to go out parallel. So already I'm going to see a slight problem here. And that slight problem is that these two rays don't intersect. So if they don't intersect on the real side of the mirror, what I'm going to do is extend them backwards into the mirror. We had the same issue with the plane mirror, but we just kind of skipped right by it because we kind of knew what was going to happen with a plane mirror. So if I do the same thing for the one that's going through the center, you can already start to see I'm expecting an intersection around there. Just to check, the one that went in parallel should go out, not through F, because that's not going out, but from F. So like this. If I extend that back, it also seems to connect here. So in this case, my image is virtual, because it's made from these extended rays. It's upright, right? Bottom is still there, top is still here, and it's shrunk. Now, I bet you're itching at this point for like, I know it's great to make pictures, but man, can we get some math in here? And boy howdy, do we have some math in here. Here is our mirror equation. It's going to relate the object distance, the image distance, and the focal length. So 1 over the object distance plus 1 over the image distance equals 1 over the focal length. We're also going to be able to talk about how big the image should be using this expression for linear magnification. So the magnification of our image is going to be the image height over the object height. That's kind of the definition of magnification. If something is magnified to be twice as big, that means the image is twice as big as the object. And it turns out we get this relationship between the magnification, not only related to the size of it, but to the object and image distances. So it's the opposite of the image distance over the object distance. The opposite is important. Magnifications can be positive or negative. This is an example of a positive magnification. Even though it's smaller, it's upright. The upright bit is what makes it positive. This is an example of a negative magnification. Negative, not because it's smaller, but because it's inverted. All right, and so let's see one more example here. A 2 centimeter tall object is placed 5 centimeters away from a concave mirror with a focal length of 10 centimeters. How big is the image and where is it? So, what I've done here is set this up roughly to scale. I'm only going to draw 2 of the rays this time because I'm going way over. Here is the one that goes, so from the point on the top, not through the center, but from the center. So I can just kind of connect this whole thing along. I know it goes in and then back out. And then I'm going to draw a second one from the focal point instead of through the focal point, but it's along this line connecting the focal point and the top. This one bounces out parallel. Nope, I don't want to do any of that. I just want to draw my line. I just want to draw. Now, if I look at these, I'm seeing here, these aren't going to intersect, so I need to extend them back. So right away, I'm expecting a virtual image. Also, right away, I know how big it's going to be. That's kind of cheating. So, come on. There we go. Extend this one back. Oof. Extending is hard. So somewhere around there, let's say. So this thing appears to be virtual. It appears to be upright, and it looks like it's magnified. If this thing is 1, 2, 3, 4 blocks tall, this is 1, 2, 3, 4, 5, 6, 7, 8 blocks tall. So that's what we expect to see. Something's twice as big. Let's see how the math works out. We're starting with our mirror equation. I want to find where it's going to be because I know ultimately, right, if I want to know how big this image is and I know how big the object is, I need where the image is because I know where the object is. So if I take this thing, I got my focal length, I know that, I know where the object is, so I need to find the image distance. So I'm going to solve it for the image distance, but I got to be careful because fractions are tricky. So the focal length is 10 centimeters, the object distance is 5 centimeters, 1/10 minus 1/5 is negative 1/10, right? 1/10 minus, well, 1/5 is 2/10. So 1/10 minus 2/10 is negative 1/10. But now this is 1 over the image distance, so I need to flip both sides. So the image distance is negative 10 centimeters. This negative is because it's virtual. So when an image distance is negative, it's a virtual image. But now I've got to take this thing over here and look at the magnification. So the magnification is minus the image distance. So this is going to be 10 centimeters divided by the object distance, 5 centimeters, which gets me 2. So twice as big. So the image should be 4 centimeters tall, or 8 boxes. Now this is a lot to take in. We've seen now most of the major examples here. Concave, you can see a lot of weird stuff happens with concave mirrors because that one was large and virtual. Convex was small and virtual. But this concave was real and small. So like concave mirrors are tricky things. We'll do some more practice drawing these things and setting these things up. But, you know, this is the thing to focus in on right now, categorizing them and then using the algebra. Have fun.